Welcome to the presentation of our work, Unsupervised Part Discovery from Contrastive Reconstruction. This work is done in collaboration with Laina, Christian Rupprecht, and Andrea Vedaldi from the Visual Geometry Group at the University of Oxford. Unsupervised learning in computer vision has the grand goal of learning as much about the world with as little supervision as possible. Naturally, we want to learn not only about the objects but also the parts they consist of. This is useful because parts exhibit higher invariances to geometric and photometric changes in the scene and can be used to improve higher level tasks. Discovering parts automatically without expensive human supervision is challenging and has recently gained the interest of the community. Part segmentation methods take an image and predict a set of binary part masks that are semantically consistent. That means that, for example, the first part always corresponds to the head of the bird, independent of the input image. To do this, one can use a standard segmentation architecture. However, in absence of ground truth annotations, we need to define a proxy task that trains the network without supervision. Before we can devise such a proxy task, we need to define what precisely is meant by the term part and what constitutes a good part segmentation. There are many possible definitions of a part depending on the context and the task, although in all variations the object is formed as the union of all parts. There are two main lines of work in unsupervised part segmentation. The first uses Gestalt's law of common fate, which states that what moves together belongs together. This line of work learns to group pixels from videos using motion as a cue. However, these approaches would struggle to segment an object into its parts when all parts move together as a whole. For example, the parts of a moving car or the example in this short video. Thus, a second line of work approaches the problem using appearance cues to define parts, learning part segmentations from semantic correspondences across a collection of images. The challenge here is to re-identify the same parts across different instances. Our method follows the second principle. Based on this definition of part, we define four simple criteria. First, part masks should contain uniform information within. Second, a part needs to be consistent across different images while being distinct from other parts. Third, the part should be robust to geometric and photometric transformation of the image. Fourth, intrapart appearance should be visually consistent. We transform these criteria into four losses, namely feature loss, contrastive loss, equivariance loss, and visual consistency loss. Combined, they form the objective function of our proxy task. Now we will describe each loss in more detail. The feature loss encourages mid-level and high-level image features to be similar to each other within a part. We first extract dense feature embeddings for the image using a frozen pre-trained VGG network. In the beginning of the training, the predicted masks do not have much in common with the actual parts. Similarly, the extracted features within each part are very dissimilar. The feature loss then encourages the masks to correspond to local clusters in feature space. This is implemented as minimizing the distance between the mean feature of each part mask and each individual feature within the same part. The second objective, the contrastive loss, acts across instances in a batch. The idea is that each object consists of the same parts, and the same parts across instances are more similar to each other than the other parts. Thus, in the embedding space obtained by the feature encoder, the mean feature of the parts with the same label should be pulled together, whereas parts with different labels should be pushed apart. Again, the features are frozen and only the masks are learned from this loss. Equivariance losses are used in many unsupervised applications to encourage the model to adhere to the geometric transformations of the image. The idea is that a transformation is applied to the image. That could be a rotation, flipping, color change, or similar. Because the semantic content of the image stays the same, we can enforce consistency by minimizing the difference between the prediction on the transformed image and the transformed original prediction. As we are dealing with probabilistic part assignments, we minimize the error with a KL divergence loss. Finally, we find that parts often exhibit a visual consistency as well. We introduce a simple form of visual consistency loss by reconstructing the image as a cartoon by applying the average color of a part to the whole mask. Minimizing the difference between the cartoon and the real image is a very helpful training signal to learn about the exact spatial extent of the parts as it tends to adhere to the image edges as part boundaries. We test our approach on a wide range of categories such as birds, humans, horses, buses, and cars. We train a separate model per category. Here we show some results on the cub dataset consisting of 200 bird classes. We find that the predicted parts are semantically consistent across images and can even be named. Red head, yellow wings, green belly, blue tail, even though no supervision has been used. Here, on the images of deep fashion dataset, we find that our method is more consistent and semantically meaningful than the previous work. For example, it learns to distinguish between skin and hair, whereas Scopes seemingly splits the head in upper and lower parts. Pascal parts is a smaller dataset and more challenging. Nonetheless, the learned parts are semantically meaningful and consistent across instances. For example, the model discovers the heads, backs, and legs of the animals, identifies the wheels of the motorcycle, and can distinguish between the front and the sides of the bus. A comprehensive quantitative evaluation, more baselines, and comparisons can be found in the paper. Thank you for listening.